Welcome to Power Electronics Education Electronic Book, Lecture 8, DC-AC Converters. This lecture is presented by Dr. FIRUZ ZARE. So let's start with unipolar modulation. So as I mentioned before, in unipolar modulation, the output voltage is changed between 0 and positive or 0 and negative. So in this case, we have 4 different switching states. So let's start with this switching state. That means the output voltage is positive. S1 and S4 are on. S2 and S3 are off. So in this case, if you look at the current waveform, for example, for this period, the output current is negative while the output voltage is positive. So basically this is the case for this time, because output voltage according to this polarity, the output voltage is positive because this switch is on, this switch is on, and because the current is negative, so in this case current passes through these diodes. But from here to here, still the output voltage is positive, but current is getting positive. So according to this direction, we can see that IGBT in this switch and IGBT in this switch are on, so they can carry the current. So in this case, this is the current loop for positive current. So let's start when the output voltage is changed to 0. So in this case, suppose the switching state is 1, 1 to get 0 voltage. So when the current is positive, here we can see that the current passes through this diode and pass through the switch. So at this stage, suppose the voltage drop across the switch is 0. That means the output voltage is 0, which is basically given here. So when the output voltage is getting negative, so this is the switching state, that means S2 and S3 are on, S1 and S4 are off. So in this case the output voltage is negative, but for this period here we can see that the output current is positive. So if output current is positive and output voltage is negative, so this is the current loop. That means current passes through the diode. Here again pass through the diode while the output voltage is negative. So this is the output voltage which is connected to plus VDC. But from here, when the output current is getting negative, so in this case current passes through this IGBT and this IGBT, and in this case here we can see that the output voltage again is negative and the current also negative. So the next switching state is 0, 0. That means top switches are off and the bottom switches are on. Depends on the direction of current. For example, in this case the current is negative. That means this is the direction of current. In this case current passes through this diode and pass through this IGBT. So here we can see that this is the current loop while the output voltage is 0. And suppose that the voltage drop across these switches are 0. In this case the output voltage is 0. So in unipolar modulation, even if you have single pulse, it's possible to change the frequency and RMS, because to change the RMS we just need to change the pulse width. In this case we can control the RMS of output voltage. So different voltage, this is the fundamental, but the point is that here even we can control the frequency. But in real application, basically we increase the switching frequency to improve the quality and reduce the harmonics. So in control section, basically we have two comparators, one for leg A and the other one for leg B. So we have two sinusoidal voltage waveforms, one for phase A, the other one with 180 degree phase shift for phase B. So in this case here, by increasing the switching frequency, we can have more pulses, and definitely we can reduce the harmonics and improve the voltage and current waveforms. So here we have voltages for leg A and leg B, and also output voltage, which is basically leg A, the voltage of leg A minus voltage of leg B. So we can look at the output voltage. For example, when leg A has 50 volts, here leg B has minus 50. So here again we can see that output voltage is 100, which is basically here. But for this period of time, the output voltage is in leg A is 50 and in leg B is also 50. So that's why the output voltage is 0. And again here we have 100. So that means that based on this pulse pattern, we have changed the effective switching frequency, because here we have two pulses while here we have one pulse. So that's why in unipolar modulation we expect to have better quality, and the reason is that we change the effective switching frequency. So let's see the effect of switching frequency. So when the switching frequency is low here, we can see that this is the ripple on output current, and when we increase the switching frequency, we can see that the output current is almost sinusoidal with very low harmonics. So a drawback again is that this one has more losses compared to this waveform, but the advantage is that this one has a better quality. And now let's compare a unipolar modulation with bipolar, with the same voltage level and with the same switching frequency. So if you look at the unipolar, so we can see that this shape is better than this current waveform. This one has significant ripple, and the reason is that when we have, for example, for this interval, when the output voltage is positive, so the current is increased, and again the output voltage is decreased to minus 100. That's why the current is decreased significantly. While here, if you compare here, for this short time the output voltage is 0, so current is 0, and then the voltage is 100, and then the voltage is 0. So because the voltage is 0, we have less reduction in load current, and then the voltage is plus and then 0. So here we can see that even the number of pulses per one cycle is more than this method. Another advantage is voltage stress. That means when the switch is on and off, this is the voltage stress across the load, which is basically 100. So while here the voltage stress is 200, that means changing from minus 100 to 100 is 200. So in a three-phase system we have three legs: leg A, leg B, and leg C. And because we have three switches, then we have 8 different combinations. So in this case we have 8 switching states, which is called 0, 0, 0. That means top switches are off, so definitely bottom switches are on. 001 and so on. So here we can see when the switch is on and off, we have different voltage at these terminals with respect to neutral point, this point, which are given in this table. So let's start with different switching states and also look at this voltage waveform when the switching frequency is low. That means we have only one pulse for each phase or each leg. So this is the gate signals for these switches. That means for the first interval, which is given here, G1 is sent to S1, so this one is on. There is no gate signal for G2, that means this is off. G3 is off. G4 and G5 are on, and G6, that means this switch is off. So in this case, if you look at this terminal, so this voltage is plus VDC because this point is connected to plus VDC over 2, so that's why we have plus VDC. This terminal is connected to here, that's why we have minus VDC over 2. And this terminal is connected to this point, that's why we have plus VDC over 2. So in next interval here, we can see that the switching state is 100. That means this switch is on, that's why we have gate signal for S1. So S2 and S3 are off because there is no gate signal. S4 is on, that's why we have gate signal. S5 is off, that's why no gate signal, and S6 is on. So again, based on the direction of current, here is the current loop, and in this interval we can see that leg A again is connected to this point, that's why VAO is plus VDC over 2. So leg B is connected to this point, that's why the output voltage is negative VDC over 2. And leg C now is connected to this point, which is minus VDC over 2. We can look at next switching state, which is 110, which means S6 is on. So in this case here we have gate signals for these top switches, so that's why this voltage, this terminal is connected to this point, which is shown here. Phase B is also connected to this terminal, which is plus VDC over 2. And phase C still is connected to this point, which is minus VDC over 2. So in this switching state, 010, this switch is off, this switch is on, this switch is off, and here we can see the gate signals for S2 and S3 and S6. So when this switch is off, so this terminal is connected to this point, so that's why the output voltage for leg A is minus VDC over 2. So leg B is connected to this point, that's why the output voltage is with respect to this point is plus VDC over 2. And leg C still is connected to this point, that's why this voltage with respect to this point is minus VDC over 2. So if you look at the next switching state, which is 011, again this switch is off and these switches are on, and these are the gate signals for S2, S3 and S5. And again, because this terminal is connected to this point, the output voltage with respect to this point is minus VDC over 2. Phase B and phase C are connected to this point. Leg B and leg C are connected to this point. That's why the output voltage with respect to this point is plus VDC. And this switching state here, these switches are off, and S2, S4 and S5 are on. That's why we have gate signals for these switches. And again, this terminal is connected to this point. The output voltage with respect to this point is minus VDC over 2. Again, same for leg B, minus VDC over 2. But leg C now is connected to this point. That's why this voltage with respect to this point is plus VDC over 2. So here we can find the line voltage, which is basically leg A minus leg B for this line voltage. And here we have also line voltage for other legs. So in this case, the output voltage is at low frequency because we have one pulse over one cycle. So it's possible to increase the switching frequency to improve the output voltage and reduce the harmonics. So in this section, I'm going to describe the active and zero vectors. Basically here, this switching state, which is 1, 1, 1, that means the top switches are on. But the point is that these legs are connected to each other, so that's why we have no source, voltage source appears across the load. We call this switching state as zero vector because this switching state doesn't provide any voltage for any phases. So it's almost same for this switching state because in this case the top switches are off and the bottom switches are on. And here you can see that leg C is connected to leg B and leg A. So that's why again these switching states 0, 0, 0 or 1, 1, 1 are defined as zero vectors. And the other switching states like 1, 0, 0, 1, 1, 0, 0, 1, 0 and so on are defined as active vectors. We have this concept in space vector modulation techniques, which is very common because we transfer the ABC coordinate to DQ coordinate, and then we have active vectors in this coordinate to be able to generate the output voltage. So in control section, similar to unipolar, we have carrier signal here, which is triangular waveform for 3 legs. So in 3 phase, because we have 3 phases, phase A, phase B and phase C, or we can say leg A, leg B and leg C, then we need to have 3 control signals. So this is sine wave for leg A, this is sine wave for leg B with 120 degree phase shift, and this is control signal for leg C with 120 degree phase shift with respect to this one. So then we get control signals for S1, S3 and S5, and also S2, S4 and S6. So again, we can compare low frequency and high frequency signals. Here we can see that the switching frequency is low, but here switching frequency is high. But I would like to describe the leg voltage, line voltage and phase voltage and also common mode voltage. Because here we have leg voltage, which is basically changing between plus and minus. Here we have line voltage, which is basically, for example, leg A minus leg B. And here we have phase voltage and common mode voltage that I'm going to describe in next section. So what's the effect of switching frequency? So increasing switching frequency here, we can see that we can improve the current, reduce the harmonics, but again a drawback is to increase the switching losses. So let's start with leg voltage, line voltage, and common mode voltage. So in this case, we can define phase voltage, which is VAN. That's the phase voltage for leg A, which is given here, VAN. We have this common mode voltage, that means this voltage with respect to this point, which is defined as VNO, and we have also leg voltage, VAO, which is given here. So this voltage equals to this voltage plus that voltage, which is given here. It's same for leg B, that means leg B equals to phase B plus common mode voltage. Same for leg C, phase C plus common mode voltage. So when we add together, on the left hand side we have sum of leg voltages, and on the right hand side we have sum of phase voltages plus 3 times of common mode voltage. So this voltage is 0 because the sum of phase voltage are 0, and in this case common mode voltage equals to leg A voltage plus leg B voltage plus leg C over 3. So in this table we can see all switching states. Basically we have 8 switching states. This is the switching state for 0 vector. Also this one is switching state for 0 vector, but these are active vectors. That means switching states in which the output voltage has at least one power supply. So based on leg voltages which are given here, so we can find the output voltage and we can find the phase and common mode voltage. Common mode voltage means the start point of the load with respect to neutral point, which is given here. So in this case, let's start with common mode voltage. So when we add together divided by 3, this is the magnitude of common mode voltage for this switching state. And if you add these voltages, which means this one can cancel, so minus VDC divided by 3 is minus VDC divided by 6. In this case, this one and this one can cancel, which is given here. In this case, this voltage and this voltage are cancelled, and here VDC over 2 divided by 3 is VDC divided by 6. This voltage can cancel each other, minus VDC divided by 2, which is divided by 3. Again here we have minus VDC divided by 6. This voltage can cancel each other, so that's why we have VDC divided by 6. Again here we have plus VDC divided by 6, and then add together divided by 3 we get this DC voltage. And now let's look at the phase voltage. So phase voltage, for example for phase A, is leg voltage minus common mode voltage, which is NO. Let's start with, for example, this switching state. So in this case, leg voltage is minus VDC divided by 2 minus common mode voltage, which is minus VDC divided by 2. So that's why the phase voltage is 0. Let's look at, for example, this one. Again here the leg voltage is plus VDC over 2 minus common mode voltage, which is VDC divided by 6. So here we can find the phase voltage, which is VDC divided by 3. So we can find the phase voltage for other switching states and other phases according to this equation and similar equation for other phases. So what is dead time in an inverter? Basically, when we look at one leg here, when the top switch is on, the bottom switch should be off. But in real case, because of switching time, which takes probably fraction of microsecond, that may short circuit the capacitor through the legs. So that means we need to switch off both switches for a while, which is defined as dead time, and then switch off and switch on. So let's start with an ideal case. That means the switching time is almost nothing, 0. And in this case, we turn off S1 here, and at the same time we turn on S2. So in this case, we can see that the voltage is changed from this position, because before it was plus VDC over 2, and now we turn off and turn on. So in this case, probably we can't see any problem because we have ideal switches. But when we have real switches, because of switching time, when we turn on and turn off, that means we have short circuit in this loop. That means discharging the capacitor through these switches. So to prevent this issue, to solve this problem, we can switch off both switches and then switch on the other one. Let's start at this point. So here it shows that this is for switch 1, this is for second switch, S2. So during this time, S1 is on. That means this point is connected to this terminal. So we have VAN. Suppose load current is positive. So in this case, current passed through the IGBT. Now at this time, we are going to switch off this one. So in normal case, we switch off and switch on the other one, but to prevent any short circuit, once we switch off, we are not allowed to switch on that one. So we should turn on after this blanking time or dead time. So in this case, what's happened? When we switch off, because the load current is continuous, so that's why in this case the current passed through this diode. So because the current is positive, so that's why it passed through this diode. So here we can see that because we switch it off at that point and none of the switches are on, you can see that there is no gate signal. So that's why, because the current is positive, this diode conducts. So that's why this point now is connected to this terminal, which is minus VDC over 2. So in this case, even if we, at this point, even if we have a signal for this IGBT, because current is positive, so that means current passed through the diode, it doesn't affect the output voltage. So there is no problem. But at this point, we are trying to turn on the other switch and turn off S1. So here we can see that, for example, when we switch off, so both switches are off. So here you can see there is no gate signal. But because still the current is positive, so that's why still current passed through this diode. That means we keep the voltage negative, and then we turn on this switch. So once we turn on it, then it can pass through this IGBT, and then we get positive voltage. So this is the scenario for the case that the current is positive and then we can analyze for the case that the current is negative. So because the load current is negative, here we can see that the leg voltage is connected to this point when the switch is on. That means basically current pass through the diode. And when both switches are off for this period, you can see that there is no gate signal either for S1 or S2. So because of this direction, so current still pass through this diode. That means we have this voltage. And once we decide to turn on the switch S2, in this case current pass through this IGBT. So in this case this voltage is connected to this point, which is minus VDC over 2. So now at this point we decide to turn off S2, and again for this period both switches are off. But because of direction of load current, when this switch is off and also this switch is off, because of this current, the current pass through this diode. That means the leg voltage changed to plus VDC over 2, and then at this time when we turn on the S1, in this case again current pass through this diode because this IGBT cannot handle. So that's why here we can see that the shape of output voltage is changed because of dead time control. In hysteresis current control, we measure the load current and we compare with reference current, and basically we shape the load current based on the reference current by changing the switching state. So in this case, basically when we try to change the switching state, we change it based on this error. So if the error is positive or negative, that means the output voltage should be positive or negative. So in this case we use bipolar modulation, because in bipolar we have two switching states, either 1 0 or 0 1, which gives plus VDC or minus VDC. And if you look at the current through the load, suppose that the resistance is pretty small, then the voltage across the inductor is L di dt, or the voltage divided by inductance value is the IDT. So when the output voltage is almost equal to voltage across the inductor, suppose R is pretty small, compared to inductor, then output voltage divided by L equals to the IDT. In this case we have two different the IDT. Either the IDT is plus VDC divided by L, or the IDT is minus VDC divided by L. That means this is negative and this is positive. It's a good concept that we can use it for hysteresis current control, because in hysteresis current control we have reference current IREF. We like to shape the load current similar to IREF, and in order to have switching we define upper band hysteresis band and lower hysteresis band. So the hysteresis band height can define the switching frequency. That means when the load current crosses this band, we should decrease the current. Decrease the current means negative the IDT. That means we should have negative voltage. And when the load current crosses the lower band, we should increase the current. That means we need positive DIDT, or the output voltage should be positive. So now let's look at the output current and output voltage for hysteresis current control based on bipolar modulation. The reason that we use bipolar because it's very simple, because in bipolar we have two switching states, which is basically 1 0 and 0 1, which generate positive and negative voltages across the load, and that correspond to positive DIDT and negative DIDT. So that's why it's quite easy to decide which voltage we need based on the load current. The DIDT is positive, that means current is increasing, and the reason is that output voltage is positive. And when we cross the upper band, so the aim is to keep the current between the bands, and when we cross the upper band we need to decrease the current. So decrease the current means we need negative DIDT, that's why we have negative voltage, and then positive DIDT and negative. So by changing the hysteresis band height, we are able to improve the quality of output current, but the drawback is that we may increase the switching frequency. It's possible to use unipolar modulation, but the case is that the control circuit is more complicated than bipolar. Basically, in unipolar we have 3 voltage levels, which is 1 0 0 1, and also 2 switching states for 0 voltage. But the case is that because we have 2 bands, 2 hysteresis band, we cannot detect how to select this switching state. So in unipolar modulation we need to have another band, another upper band, and another lower band. So now we have more bands, and then based on a state machine we can detect whether we need to increase or decrease the output voltage. So that's why in unipolar modulation definitely we can get better quality, less switching losses, but control circuit is more complicated.